¿vale? Y
imagino que esto funcionará.
Aquí, vale, déjame ver cómo se ve lo que dice ahora. Y aquí lo que hago es en anclaje aquí, ¿vale? Bueno, no sé si eso es una buena idea, creo que sí, porque ahora cuando me vaya al Zoom, cuando me vaya al PowerPoint, debería ya estar.
Vale.
Aquí había un pincho USB, ¿lo
Sí.
tienes?
Lo tengo yo.
¿Estás
Sí, un momento.
entendido?
Sí. Creo que lo había
A
usado
ver,
antes.
espérate, vamos a comprobar. ¿Alguien que esté en Zoom, por favor, me puede confirmar que se oye bien? Sí. Vale, gracias. Pues creo que puedes empezar ya.
Vale.
La presentadora.
So, good morning, everyone. Sorry for the delay. Today we have Dr. Roca-Fàbrega, which is now in observatorio.
Lund.
University.
Observatory.
Lund University. Lund Observatory.
Yep.
Lund University, and he has been in Barcelona doing the PhD, and then he went to Israel and Santa Cruz, and then he came here to the UCM during 4 years? 5 years. 5 years. Finally, he has a research engineer position at the University of Lund. Today, he's going to talk about, let me see, first results on Harkonnen simulations and a bit about galactic dynamics, because he's an expert in cosmological simulations. He's the coordinator of the Agora project and also the coordinator of the simulations in the Arrakihs mission. So, Santi, please.
Okay, thank you. Thank you a lot for inviting me and allowing me to present these results here in this seminar. Most of the results has been done obviously by many people in the Harkonnens, including several postdocs and PhDs, some of them even here in the audience. And the second part is mainly the work of a PhD student that we have in Barcelona with Mercè Romero Gómez, that is very novel results about invariant manifolds that many people here in the Complutense University have heard about, because when I was teaching here, I was trying to convince everybody about the invariant manifolds. Oh, no me gusta. So I will talk about these two things. It's 23 slides. I hope I will not be very long, but also if you want to interrupt me at some point with questions, also feel free if there is something that is not clear. Okay, so let's start with the first. In fact, I should have started this while I was introducing the presentation. This is already the first movie we produced from the Harkonnen simulations. You will see in this presentation a bit more about how this simulation evolves and the potential that the Harkonnens big suite of simulations will have in the future. Quite far in the future, but we will get there at some point. But yes, this is just a first example on the gas temperature produced from a galaxy that is a Milky Way-like galaxy that is in the very center of the simulation. I will go in more details about what is being shown here and how good is the resolution and the things that are being produced in the simulation. But well, starting with the motivation of the Harkonnens simulations, first background, the people that has been working a bit in simulations or at least understands a bit about how simulations work in the community, you will probably have seen already this figure here. This was a paper, a review talk about simulations, about cosmological simulations by Vogelsberger in 2019. Obviously, in the world of simulations, everything gets outdated very fast. So most of the simulations that are here are now probably considered low resolution, although many people is using, especially, for example, Illustris or TNG. These are simulations that are quite commonly used in the community, but gets more and more low resolution as the new physics implemented in the codes and the supercomputer powers increase. No? I added some newer simulations here on that site, to give you a bit more of the feeling of the resolutions that we are dealing with now in the community. In big volumes, the resolution is still pretty bad. When I talk about resolution, I mean the minimum mass of stellar and gas particles in the simulations. That is what gives you an idea on what can and what cannot be simulated. For example, a cluster of stars that has 1,000 stars, 10 to the 3, you cannot simulate it in a simulation that has, for example, a mass resolution of 10 to the 3, because basically it would be a single particle being in this cluster of stars. No? So this is a bit of the idea of why it's so important to take in mind the resolution, both the mass resolution, that is the one that you see here labeled like baryonic mass resolution, but also the spatial resolution, that is the one it's not included here. Okay, I have not included here. Well, the spatial resolution is the one of, in the SPH codes, what is called the softening, that is in the range in where you can trust the gravity. In the AMR codes, the ones that use mesh, is the minimum size of a cell in where you compute the variables of the simulation. Then everything that happens in smaller scales than that, you cannot trust it, because you are not using the real gravity for the computations that you are using in the simulation. When we talk a bit about big volumes, you can see that the resolution is pretty bad if you want to talk about galactic physics. That is about 10 to the 9, 10 to the 7, 10 to the 5, some of them. This means that you can really not resolve clusters of stars, or even very big clusters of stars in the disk of the galaxy. And these ones, in fact, the spatial resolution is in between hundreds of parsecs and kiloparsecs. That means that you are not resolving, for example, the scale height or even sometimes the scale length of disks. So everything that is related with disk formation and thin disk formation is quite complicated to analyze with big suites of large volume simulations. For that, what we usually use is what is called the zoom-ins. For example, here you have two examples. I selected especially these two here and also the horizon here, because they're the ones that the work that we are doing in HARKONENS is based on. You can see that in zoom-ins, you can start reaching resolutions on mass that is about several times 10 to the 3, and the spatial resolution that is not labeled here is tens of parsecs. Then you can start doing stuff with disks and internal structures of the main galaxies. Still, only simulations that are zoom-ins, that means leaving everything else at lower resolution and focusing the high resolution in a very tiny patch in the center of the simulation, you can only reach resolutions of about tens of solar masses, that then this allows you to study properly formation of clusters of stars, in cases when the zoom-in is around a dwarf galaxy. In Milky Way mass galaxies, there is nothing in the community now with a resolution as high as that, to be able to resolve the formation of, as I said, clusters of galaxies, or more importantly, like you will see now in the next slides, streams of stars, for example, disrupted from dwarf galaxies. So, and why is important to get better resolutions to what we are having now in the community, in the state of the art? Well, there are several papers that show you why you need very high resolutions, or resolutions at the level of 10 to the 3 solar masses for the stellar component. One of these is, for example, the paper from Nora Ship in 2023, in where both analyzing data from observations in the Milky Way of the dwarf galaxies and streams in the Milky Way, but also focusing on high-resolution simulations at the time from the FIRE collaboration. You can see here, as a function of the stellar mass, the total number of streams, satellites, or the combined stellar component. And you can clearly see that there is a threshold here in the simulations that is basically at several times 10 to the 5, about 10 to the 6, in where the simulations are really not able to resolve the formation of anything, and is in where most of the stellar streams are located. So you see that this is one stellar stream, this is 2, 3, 4, and above the larger number of streams comes from smaller masses than the 10 to the 6. Then you really need resolutions of about 10 to the 3 to have 1,000 particles in a very long stream around the central galaxy. This motivates a bit why, if we want to study stellar streams, we need really to go to very, very low resolutions. Similar thing happens with the amount of dwarfs. Most of the dwarfs peak in resolutions in where the models that we have available now, the models of Milky Way mass galaxies that we have now, do not resolve the formation of this kind of dwarf galaxies around the Milky Ways. Another thing that we discovered within the Arrakis consortium, one of the members of the Arrakis consortium, a PhD student in Santander, is basically showing that most of the observable streams come from masses at about 10 to the 7, 10 to the 8. solar masses of the central galaxy, and this means that also that we require this high resolution to start resolving the formation of this kind of streams. Another reason for having higher resolutions, if now we move in the low surface brightness universe, HARKONENS I have not introduced, but is the Arrakis simulations. Arrakis is a space mission that will focus on observing low surface brightness structures. That means stellar streams, the intra-halo light, that means the light that comes from the very diffuse stellar component of the halo, and also from the smallest dwarf galaxies. This is the case I'm showing here in this plot, another of these low surface brightness variables, that is the intra-halo light. And you have the amount of mass in the what we call ex-situ stars, that are the ones that then became part of the intra-halo light as function of the stellar mass. For a Milky Way halo, we are about at this value several times 10 to the 9, and you can imagine that this several times 10 to the 9 stellar mass, solar masses is distributed along all the entire stellar halo of the main galaxy. Then this means that if you have a resolution of 10 to the 5, if you distribute this 10 to the 9 in a full halo with particles of 10 to the 5, you will see absolutely nothing as a diffuse stellar halo. You will just see small patches with big particles, stellar particles distributed, scattered around the halo. So it's very important to reach very high resolutions to be able to trace the distribution of diffuse light that comes from stellar halos around Milky Way-like galaxies. It's another reason for why we need higher resolution simulations than the ones that are available now in the community. And a final one, another of the goals in Arrakis, and also a goal in the community in general that is being pursued, is trying to distinguish different predictions from different dark matter models. This is a very simple model by Mastacci 2023, in where you have the distribution as a function of the mass of the dark matter halo, the amount of systems you would have. And the most important part here is the region in where you can start distinguishing between different dark matter flavors, especially the 3 kiloelectron volts and the 10 kiloelectron volts warm dark matter. That is in where more or less we have still not discarded the models for dark matter, for warm dark matter. Things that are below 7 kiloelectron volts are mostly proven to not be correct from particle physicists and also by microlensing observations. So in between 7, 10, that is basically this dotted and this dot dashed line, here in this regime of total masses for the central halo in about 10 to the 7, that this means 10 to the 5-ish in stellar masses is in where you have the potential of discovering differences between dark matter models that are still not discarded. Then really we need simulations in where the minimum baryonic mass is 10 to the 3 or lower if we can. And this is not available now in the community for Milky Way mass galaxies.
Sorry,
yes?
Why is it we have less structure for cold dark matter than from warm?
No, so cold dark matter is the solid one. So
the top one. Okay.
Exactly. So it's the one that exactly this other solid colored is I don't know which one. It's the 0.5. So it's a thin solid line. It's not the best the best decision the authors took. Yes, absolutely. So yeah, this is the 0.5. no problem. Good question. Good. So HARKONENS. As I said, HARKONENS is I am usually selling it as a big project of cosmological simulations, but HARKONENS has two different parts. A first one that is idealized simulations to find the details on the formation of streams, the superstructure of the streams, and especially the observability of the streams. What we need is not only to resolve the disruption of the satellite, but also the distribution in the phase space of the particles or the stars once they leave the Lagrangian points of the dwarf galaxy. We cannot resolve that in any cosmological simulation that is trying to resolve a Milky Way size galaxy. Then the only solution that we have is to get insight from models that are a lot less realistic, but still, because you can control a lot more the parameters, they can provide you a better information on the details on the dependence of the different parameters that you can have in the dwarf galaxies. Say it in other words, you can run thousands of very idealized simulations in where you have, for example, a flow-zone potential for the central galaxy, and then varying the orbits of the dwarf galaxy, the properties like the density profiles, changing also the masses of the dwarf galaxy, and launching this galaxy towards this frozen potential, you see how it disrupts. And assume that in a cosmological simulation, you could choose from this catalog of thousands of simulations the specific dwarfs that will be falling towards the central potential of a Milky Way-sized galaxy. Then kind of you can make a statistical study on how the disruption would occur just by taking these very, very high resolution simulations that basically, because you only need the dwarf galaxy and a frozen central potential, you can reach a resolution of single stellar particles, like with 1 solar masses or below. Then you can really make dwarf galaxies that are with a clear, very well motivated, observationally motivated density structure. This is what we do in this first part of Harkonnens. Again, this is driven by Abraham Perez in Santander in the IFCA. IFCA? CEFCA? I am always confused. IFCA. Is IFCA. Okay, good. I am not the only one that confuses both. So he has been running tons of simulations using a code that is called Swift, that is pretty fast, and then made some mock images using a tool that is called PNBody, developed by Yves Rebats in Switzerland, in the APHL. And from that, this is very preliminary results. He has been analyzing how you can observe or not different dwarf galaxies depending on the time since the first infall, the eccentricity of the orbit, but also the concentration of the dwarf galaxy, and also, let me remember, and the mass, the stellar mass of the central galaxy. And you can see here some results at different depth, 32 magnitudes, 31 magnitudes, 30, 29. Arrakis would be around here. And each line is for a different mass of the initial dwarf progenitor. The baseline would be the vertical axis is the maximum detected area in arcseconds square as a function of the eccentricity of the orbit. And for different masses, each color is a different mass for the progenitor. And you see that the baseline is basically the area of the original progenitor before disruption. And when this goes up, it means that you increase the detection because a stream has been formed. And well, some informations that you get from here is that dwarf galaxies in the regime of 10 to the 6, 10 to the 5, even 10 to the 7, it is very hard or impossible to observe the disruption when you are in magnitudes 31, 30, 29. While, for example, the 10 to the 7, you start seeing the disruption in cases with very, very high eccentricity. So we know that very radial orbits disrupt a lot more, so you can observe them better. And while the most interesting part is in where a big part of the dwarfs that we'll be observing is this 10 to the 8 solar masses from the progenitor, that in half of the eccentricities you see very clear signal of disruption if you go at magnitudes that are compatible with what will be Arrakis magnitudes. This, by the way, is in the visible. So it's, we have 4 filters in Arrakis. This is what is called the BIS filter in Arrakis. The most massive ones, we would be able to observe some disruption in most of the cases. So this is one of the potential things that we can do. You can have a small simulation here in where you will see the formation of a stream. It's not very good, yeah. So you can see it's very small, and also with so much light is difficult to see. But it's one of the models that Abraham has been running. This regarding dwarfs, let's go the part that both parts are interesting, but I like more the cosmological simulations because it's my background usually. Harkonnens cosmological simulations. It's a pretty detailed or long, how to say, organization or with different needs that needed, things that needed to be checked for this big suite of simulations. That is basically the goal that we want with Harkonnens is to understand how streams are formed around Milky Way-sized galaxies that are the ones that we will be observing in Arrakis, with the final goal of seeing how can or not or cannot observe these streams in these galaxies and how many of them can be observed at the depth of Arrakis, but also understand how these streams form around Milky Way-like galaxies when you put a cosmological context, and in which situations the same dwarfs would generate a stream or not. So it's a bit trying to understand how the mass of the galaxy has been accreted, how the dwarfs that has been carrying this mass have been disrupted, and if from what we see, these streams, these disrupted dwarfs, we can get some information about the past of the galaxy. All this is what we want to learn. You can only do that with simulations in where you control all the process since the high redshift, like redshift 100, that is in where the simulations start, till redshift 0, and if you have enough high resolution. For that, I have been insisting, we need high resolution, as high as possible. The bottleneck on that is not the simulation itself is technological in terms of CPU time. If we had infinite CPU time, we could simulate the entire universe if we wanted. In this case, we are limited by the supercomputers that we have. And we are trying to push the resolution as high as we can with a Harkonnen suite for a Milky Way mass galaxy. The resolution that we are targeting is 20 parsecs in a spatial resolution. We have AMR and SPH codes. This means the minimum cell size of the AMR codes in where you use a mesh, or the softening length, it would be 20 parsecs in softening length, 40 parsecs in softening length, and the mass resolution is 10 to the 3 for the stars and 10 to the 4 for dark matter. I will not enter in the details in the difference between the dark and the stellar component, but also within the Arrakihs, the COST team, the one that I am coordinating, we checked that a difference of 1 order of magnitude is not producing something that is called numerical heating that could like blur our results. Okay, so we are fine with the difference of 1 order of magnitude between the baryonic resolution and the dark matter resolution. And these are some of the results that I can show you on the difference between having the state-of-the-art resolution, Agora. Probably the people here have heard about Agora. Agora, I have been coordinating it to produce a big suite of simulations with the state-of-the-art resolution that is now no longer so state-of-the-art, 80 parsecs in spatial and 10 to the 4-ish, a bit more than like 3 times 10 to the 4, 4 times 10 to the 4 in the stellar component. And you can start seeing how big the difference is on the amount of substructure that can be generated around the Milky Way size galaxy. So this is the Milky Way size galaxy with all these interactions, all these thin streams that appear everywhere that you can really not resolve if you have the resolution of. Agora is better resolution than TNG, much better resolution than TNG that everybody is using, and at the same level of resolution of, for example, the Auriga galaxies, that is also another suite of simulations that the people is using. So with the traditional or most commonly analyzed simulations, you can really not track all these details on the formation of streams that you will be able to track with the HARKONENS suite of simulations. Just this is really coming out from the oven right now, so it has not been shown before. Is the potential of the HARKONENS simulations. Another busy plot. I will just go in the details broadly, not in each one of the panels. One other thing that we needed to be super sure when configuring and when thinking on the HARKONENS simulations is that the codes that we use and the physical prescriptions that are being used have been demonstrated. It has been demonstrated that they really reproduce observations, especially on the dwarf regime, that is the one we are interested on. So in the case of the main part of the suite of HARKONENS simulations, we will be using a code that is called Ramses. It is an AMR code. It's very good so the AMR codes are very good when tracing regions with very low density. That is, in fact, is the region of the halo, because AMR codes use a mesh for computing gravity, for computing also the hydrodynamics. SPH codes use particles, and if you use particles, it's much more difficult to reproduce a distribution than if you just use a mesh in where you interpolate between the nodes of the mesh. No? So we are using Ramses for the main part of the simulations, and the feedback and physical scheme from the edge simulations and combine it with the Wintergatan simulations, both of them demonstrating in most of the main properties of dwarf galaxies, observed properties of the dwarf galaxies, that these simulations fit very well within the observations. We have velocity dispersion as a function of the half mass radius, as a function of the magnitude, absolute magnitude in the V band, also the half mass radius as a function of the magnitude, and the dynamical mass, the mass to light ratio using dynamical mass versus the magnitude. And in all of them, in the background, you have the shadowed dots are mostly observations, while the solid dots are the ones coming from the simulations. It's true that you have this point here that is super a big outlier, but this has been done in purpose to check that if you don't use the proper feedback scheme, suddenly you are out of all the observational relations. So we have checked that with Ramses edge feedback, the dwarf galaxies fit very well in velocity dispersions, in masses, in sizes, and also in the metallicities. That is quite key, the metallicity, to predict the luminosity in different bands. Okay, so also the metallicities and age distribution, I didn't add here the age distribution, the simulations are fitting quite well with the above level observations, especially observations of dwarfs in the Milky Way. The second suite of simulations we use, we would never be able to trust 100% in our results if we focus in a single code. I am an Agora person, and I know that different codes can produce very different things. So it's good that we have more than one code making the similar analysis. And for that, we will run the same initial conditions using another code. We have an AMR code that is Ramses, and we will be using an SPH code that is Gadget 4. Is an evolution of the one that maybe some people here has been using. Is the one that was used for the Millennium simulation, if I am not wrong, the original Gadget. Gadget 4 is an evolution of this one with another feedback published by Tomaru 2026, a team in Japan, in Osaka. That also have shown in a very, very recent paper that the stellar mass for the dwarfs, the half mass radius, the metallicities in both the iron and the oxygen fit very well with the observation that is the background gray dots, and the simulation is basically the cyan dots on the top. And you can see that the relations, they proved that the relations also fit very well with the observations. So these are the two different feedback schemes and the two different codes we are going to use in our big suite of simulations. Another important thing that we needed to think about when designing the Harkonnen simulations is that every Milky Way mass galaxy, so if you take only a bin in the mass, in the total mass or in the stellar mass, are different things, but both, if you take it in total mass of the galaxy or in the stellar mass of the galaxy, a galaxy with the same mass at redshift 0 can have a very broad range of merger histories, that this would have a very big impact on how the halo has been built, how the dwarf will be disrupted, etc. So what we did is to go to a big suite of simulations, very low resolution, that is Horizon AGN. And from the Horizon AGN, we selected all the halos that have a mass compatible with the Milky Way, and we basically checked their merger histories. When we saw the merger histories, then we decided to select 50 different initial conditions covering all the range of merger histories. From galaxies that were formed very far away in the past and had no mergers since redshift 3, till galaxies that have been mainly formed in the very, very recent times, excluding things that are currently in a major merger. We are not interested in that because Arrakis is not going to observe major mergers in principle. Then we wanted to have a very broad range of initial conditions to run to just be sure that our results are not biased due to the merger history of the galaxy. And another thing that we wanted to, that is a goal in Harkonnens, is to check how galaxies change when you change baryonic physics. So at the very end, the goal of these simulations is that once you have observations, to be able to say from this big suite of a statistically significant sample of observations, I can understand which feedback processes generated the things that we observe. So trying to constrain, for example, the energy that is really released per supernovae and the way that is released, that of course, if you had infinite resolution, you would just simulate the supernovae, but you cannot. So you want to see if the subgrid physics recipes that you are implementing in your code is the one that fits very well with observations. So this is something that we want to do, and to do that, we need to have simulations with different baryonic physics. So this is also will be included in Harkonnens. We started just by changing the feedback strength, and you will see here again the gas temperature in the original Wintergatan. That is not the one that we use as a fiducial. We decided to use a bit stronger one that makes the central galaxy to be closer to the Moster and Beruzzi relation. And then we are also running 2 more simulations with a much stronger supernovae feedback to have all the possibilities to be compared with the observations in the future. Apart from the supernovae energy, we are also going to change the reionization time, the cooling and heating recipes, and many other things that we will be discussing with INCOS. The results of changing feedback not only affect the gas around the galaxies, but you have here a plot in where you see the stellar component, how with a very weak feedback, you end up with very, very extended disks, while if you put the too strong feedback, the disks are almost destroyed. And well, also the comparison of low resolution, what you would see. So in disks, you can see why, when I am saying that in Illustris or Auriga, you can really not understand very well what's going on in the disk, is because you have this in comparison with what you have if you increase resolution by 1 order of magnitude. So this is the direct comparison of low resolution and Harkonnens resolution when talking about disk formation. Yes, absolutely.
I mean, the resolution is coupled as well with the amount of feedback you want to put. No, I mean, if you have low resolution, you can put a very strong feedback because you have to share the supernova between a larger number of cells. So my question is, okay, maybe your feedback number 2 or whatever is more compatible with what you see, with the resolution you have, but if you increase the resolution, you will require strong feedback to reproduce this. Okay, so yeah.
Absolutely. So in fact, I didn't motivate why. You could have told me, well, you have done here a trick, why you are not using Wintergatan feedback? Because we have higher resolution. And the Wintergatan feedback doesn't work when you go to the Harkonens resolution. That's why we boosted it, because you are not resolving. So you are now resolving better the shells of supernovae. Yeah.
Probably because the feedback analysis the model is too high for the resolution.
Yeah. So at the very end, it's just too much both, no? And what we want is when we get the observations, we want to know that if at this resolution, which is the feedback that is more compatible with observations, and then we can make other predictions because then we match with observations at this resolution. Absolutely. Yeah. Good. So this is regarding differences on the feedback prescriptions. Very important, I have not mentioned it. We decided, because we already have 12 papers, some people here published papers in Agora with analyzing these simulations. It's quite well studied, these initial conditions, so we have kind of a baseline to compare what we observe with Harkonens with what has been already published from these initial conditions, that is the Agora initial conditions. So for the variations on feedback, we keep the same initial conditions and we only vary feedback. The other 50 different initial conditions are to check the dependence on the accretion history, not on the feedback. So it's different dimensions that we are surveying. For example, the dimension in where we will be simulating these 50 horizon AGN initial conditions is when we change dark matter. And here you have also the first example, when having a cold dark matter, the 7.5 keV warm dark matter. This is, as I said, still not discarded as a warm dark matter possibility. And here is the 3 keV warm dark matter that we are simulating it because it's a very extreme case that if you want to compare what you simulate with observations, you also need the extreme cases, although being unrealistic. No? So we have the 3 keVs. It's very small. When you go back home, you can go to YouTube and rewatch the presentations because the differences are pretty small, but it's expected that cold dark matter has a lot more substructure than when you go to a 3 keVs warm dark matter. Maybe it's not super evident in this resolution of the screen, but yeah, there is a lot more substructures in the cold dark matter. You can see it later. But we are running all these models with already 3 different initial conditions. You will see that most of the models are still not reaching Redshift 2 for this comparison of different dark matters. And we are using, because we want to keep some of the variables, we have tons of variables, we need to keep all the variables but one. Here we keep the fiducial feedback, that is the 2 times the boosted Wintergatan feedback for this specific. But still, well, I didn't saw this yet, so I am also surprised now, as maybe you are, how big substructure you see in streams when you are in 3 keVs warm dark matter compared with cold dark matter.
Well,
and
you see less, I mean, I have the
it's a bit,
you have less streams in the warm dark matter.
Yes. So, but in the 3 keVs, the streams are broader and more visible because you are not perturbing so much the dwarfs, no? So it makes sense. This is, do not copy this result. It's interesting. Yeah. It's also true that it's a slightly different redshift. Yeah, the final snapshot is not the same redshift. These 2 are almost the same, but this one is not. Yeah. Good. So this is regarding the simulation that we already ran. This is a bit the strategy. I already went through all of it. I will only focus in 2 last things here. First of all, the estimation is that we need 3 billion CPU hours for the entire suite. We are going for it. We already had granted 300 millions. We are waiting for an answer about 100 more million CPU hours in the Red Española de Supercómputo, and we asked for 300 more millions in the Europe HPC next project. The proposal is submitted. This should be just a continuation project, so we'll see. Yep, we need 10 times more CPU time than the one that we got till now, but we are going to do it. So yeah, I am quite, we need to publish papers and demonstrate that the strategy works before getting more CPU time, but we will do it. And yeah, and well, for the idealized simulations, we are also running them in Mare Nostrum, but as I said here, this is peanuts. It's 10,000 CPU hours. I have it in my drawer. Anyway, good. So, and the other thing that I wanted to mention is this thing that is very interesting but very challenging. Is kind of, I would say, for me at least, is novel. It's not novel in the community. It has been running around the community for the last 5 years, but is developing something that is called emulators. We named it Mentat because also the Dune wall, you know, Mentat people what is in Dune. So the emulators is a very powerful tool that is based in machine learning. It's a bit more complicated than that. I have a slide talking about it. I am not an expert on it, but I am getting an expert lately on it. That is basically the idea for the non-experts. If there is somebody expert here, will say that is not exactly what I am saying, but for the non-experts, it allows you, by training the machine, to end up with knowledge on how your results of a specific parameters, like for example, number of streams, length of the streams, width of the streams, observability, intra-halo light profiles, by not running thousands of simulations, but a small representative suite of simulations in where you can interpolate in the most basic approaches or learn with the neural networks, which would be the result if the parameter changes this much. Okay, I don't know if it's a bit blurred and foggy what I said, but basically is to try to avoid running thousands of simulations that would require trillions of CPU hours, to only use 3 billion and be still able to say something. This is a bit the idea, okay? And we are developing this together with teams that have long expertise on developing emulators. One group is the DREAMS team, is an American team led by Paul Torrey and Francisco Villescusa Navarro that uses neural networks. They have some thousands of simulations, and they have been training neural networks to predict some parameters, especially the resolution that they have is pretty low. They cannot resolve dwarfs of less than 10 to the 8 solar masses, but well, we can still keep their approach with now our higher resolution simulations. And also with the Artemis team, a UK-based team led by Andrea Font, in where they use Gaussian processes with simulations that cover, it's only 8 halos, but they cover a wide range of warm dark matter energies, and also a wide range of variations on the feedback processes. Also, Artemis, although being a bit higher resolution than DREAMS, is also, let's say that is a state-of-the-art resolution, like Agora. Okay, so it's still not able to produce nice streams. And a result, very preliminary result by Matthew Saylor, that is a PhD working with Andrea Font. Yeah, it's not trivial to explain. It's a lot of shaky lines. But what is important is in here that basically is depending on the, for example, in this case, the warm dark matter energy, some parameters in the feedback, some parameters on a star formation. You select a specific variable, in this case, the in situ mass fraction, outside 0.2 times the virial radius, and you see how the in situ mass fraction depends on each one of the variables. And for example, we see that there is kind of a transition in more or less these 4 or 5 keVs in warm dark matter. Then you have some idea that with the in situ mass fraction, you maybe can say something about warm dark matter. This is a bit of the more clear signal is, and is expected, is that the in situ fraction depends a lot on the density for a star formation. It has sense, no? Is the in situ is the one that forms in the disk, so it will depend on how you put the threshold for a star formation. So this is a very broad example of what can be done, and we hope that with the Mentat we develop a much better approach. It's pretty late. The HARKONENS simulation preliminary results, I will be very fast with that. You already have seen the preliminary results in the movies. This is just to show you how well at Redshift 2 for now, our fiducial model fits with Andromeda and the Milky Way. We know that this is not super representative on what will happen at Redshift 1, but at least things look good enough for the moment, both for the size of the dwarfs, for the velocity dispersions, for the metal content, and also the mass function of dwarfs. And regarding the stellar mass, halo mass function, the one that most people here probably knows, Beruzzi, Moster, etc., the semi-empirical and semi-analytical approaches for the ratio between the total mass of the galaxy and the stellar mass of the galaxy. These results are from a master thesis that is going to be presented next week, but requires of very good researchers in the room to help us with the analysis of the halo finding, because this has been done with only Rockstar and needs to be improved in further analysis. But why I'm putting this plot here is because one halo that is very well traced by Rockstar is the central halo. And the central halo, that is the Milky Way, is this one here. And basically, you can see these 3 dots is with different feedbacks, and the feedback to normal resolution is not plotted. It was in the version that I thought that I put it, but the red was exactly in the middle of the Perosi curve that you can see. It should be in the middle, so you have the blue that is the one, and you have the yellow that is the one here, so the red is around here, but it's not plotted. Well, anyway, you have to trust me that we are doing very well also with the central galaxy in the stellar mass halo mass. It's a bit a shame that it's not here. Anyway, good. And yeah, for the future, finishing with this first part, the second part will be faster. This is the future. We moved to Ramses OpenMP. That is much faster than the original Ramses. So this 3 billion may be reduced to 2 billion in the future because we use a code that is faster. And we already checked that even being a new code, it converges very well with the old code. We need to start running the gadget 4 with Osaka physics. We have not started yet. It will be in the next round of CPU time. And very importantly, you have seen only cold dark matter and warm dark matter. We are implementing self-interacting dark matter in gadget 4 and comparing it with already available self-interacting implementations in other codes, in Arepo, in Changa, etc., etc. And it's quite good conversions with it. So we will be running with gadget 4 self-interacting dark matter models also. Running more realized simulations, and also in the spirit of Agora, and in fact we plan to merge one of the big projects of Agora with Arrakihs, is to run with other codes also the same initial conditions at high resolution, using Arepo and Changa in addition to Gadget and Ramses. And well, there are many names here that are in the room, again, insisting on the students, that will be leading this part of the analysis of Harkonnens. So hopefully there will be several papers regarding the analysis of that. And also, I know that there is people in the audience online also interested in using Harkonnens for other things that is not Arrakis science. Obviously, this will be something open for the community at some point to be used for studying of disk formation, spiral arms, etc. And, for example, the thing that I am going to talk in the very last part of the talk, that is the origin of spiral arms in barred galaxies. The people that has been here in the Complutense, you know that I was working with Mercè Romero, that is in the audience, with a master student that was Victor Padura Feito, trying to demonstrate that in n-body simulations. We did some advanced, but the project was stopped at some point. And we got recently a very amazing, nice PhD student that works very fast on the analysis with very mathematical mind, that in very few months has been able to produce the results that I am going to be showing. That is really proving in a quantitative way that in a pure n-body simulations, we have invariant manifolds driving the spiral arms formation. The basics of that is that any system that is not axisymmetric, you will have, well, also the axisymmetric ones has Lagrangian points, but in the case of a non-axisymmetric one, you have a very clearly defined Lagrangian points. In the case of a barred system at the extremes of the bar, these are half unstable points, I don't know, saddle points, I think are called, and 2 directions will have, let's say, stable orbits. The 2 other sides will have unstable orbits, and through the unstable orbits, basically any particle that you put in this saddle point will follow the unstable orbits. And basically by following the unstable orbits, you would be forming spiral arms. This is what the theory says. This is what theoretical models show. When you do test particles with the potential of the bar, clearly these emerge there, but it has been never proved quantitatively that this happens in pure n-body simulations, totally self-gravitating. And the interesting part of this is that these spiral arms generated by the invariant manifolds should share both properties of the typical traditional density wave Lin and Shu spiral arms, because at the end they are a density fluctuation because they contain an overdensity and they basically travel with the same pattern speed of the bar that generates them. But on the other way around, it also contains particles, something that is not happening in the Lin and Shu approximation, where the density wave doesn't contain particles itself. It's just a density perturbation that goes through the disk. So this is a very interesting kind of density structure for the spiral arms that we wanted to test in pure n-body simulations. There were some first qualitative results that were showing that this was happening in n-body simulations. Athana Sula 2012. In my PhD thesis, we checked that also in 2014, long time ago. It was in a drawer for a long time. And now we got through the tool that allows us to recompute the potential from the n-body simulations. We can go further there and test it and quantify it. So the strategy is very, very, like say, basic or obvious, but this doesn't mean that it is easy. That is computing the potential from the simulation. From that, we can get the Jacobi energy, and from the Jacobi energy, what we can get is the details on where or which orbits will be the orbits that will be producing the manifolds, and which particles in the simulations are trapped or not within this orbit, with the unstable manifold branches, and also in the stable manifold branches. So this is a picture, a real picture of the, if I am not wrong, these are the unstable branches. This is Lagrangian point, these are the saddle points, this is the very stable point in the center of the galaxy, and these two here are totally unstable points. And you can see in the branch of unstable orbits, you can generate this kind of a spiral arm. This is extracted from the n-body simulation that we were analyzing. And these are direct results of a specific particle, selecting specific particles by the Jacobi energies. The Jacobi energy for the manifolds is very specific, so if you select it and then you track the particle, you see how the particle, this case is a particle that has the energy compatible with the manifolds, it goes inside the bar and then follows the manifold, generating a spiral arm-like shape. If you have lower energies, they are not trapped in the manifold orbits, and they are basically or disk particles that they shake when they cross the spiral arm. It looks like a density wave, or they are orbits inside the bar, like giving a strength of to the bar. And the ones with higher energies than the manifolds are particles that, or stars, that would be orbiting the unstable points just on the other sides of the, like on 90 degrees from the main axis of the bar. I already said that. We computed, we quantified how many of the stars that are in the spiral arms really belong to the manifolds. And we saw basically here, what I am showing is in this column here, plotting in colors all the particles that are with energies compatible to manifolds. Doesn't mean that they are in the manifolds. They also need to be in the proper place to become trapped to the manifolds. But all these stars here would be inside the spiral arms and following invariant manifold orbits. What we saw also is that if we go to the b theta versus radius, they generate a ridge, something that has been seen and generated by many other mechanisms inside galaxies, and this has been seen in observations in the Gaia data. Spiral arms can generate that, the bar can generate that. In this case, spiral arms that are compatible with manifolds, with invariant manifolds, also became a ridge in this space. So this would be maybe something observable. And yeah, I already talked about this one. And also what we see is positive radial velocities going through the spiral structures when they are manifold compatible. And to finish in the quantifications, and I am going to leave it here, basically what we wanted to know is, as a function of time in the simulation, if the particles that travel along the spiral arms following the invariant manifolds, if they are always there. So if spiral arms should be permanent in a galaxy that is following the invariant manifolds. That this would contradict absolutely observations, because in observations, the spiral arms, we know that are recurrent. So what we found is that, yes, the spiral arms are recurrent, so there is an oscillation of trapping by the manifolds with about 100, 200 million years between different peaks of trapping by the manifolds. That was interesting. We already more or less saw that in the past. Now it's quantified with numbers, with the percentage of trapped particles. We also saw that the disk particles, the particles with lower energy, also feel every time that there is a trapping of particles by the manifold, so they react as they would do with a density wave. And the very interesting part that is also it's very interesting that they are not aligned. So there is the peak in the manifolds and the peak in the perturbation in the disk doesn't happen at the same time. it means that, of course, the stars needs time to react from the potential that is being generated by the manifold, by the excess of particles provided by the manifolds. We are checking all that in detail and quantifying it with also with the potential, and we are trying to compute the self-gravity. Well, Tony is trying to compute the self-gravity. And this is the same as I shown before, that is these oscillations on the trapped number of particles, this kind of oscillation, and the oscillation of the A2 mode, the Fourier mode of all the particles in the disk. That is this more or less misaligned, this 50 million years with respect to the peaks on the manifold trapping. That this is something being analyzed that will be presented in a paper. Well, there is a paper 2 submitted under revision. There will be a paper 3 in where we will try to explain in a very precise way that the manifolds can explain that the spiral arms are recurrent, basically because the spiral arms self-regulate themselves. I will explain it very fast. I can talk in the next time that I come here when we will have it more already published. If you have, I have been talking about Lagrangian points. Lagrangian points are due to a potential that is a bar in the center, and let's imagine that everything else is axisymmetric, and you have very clear Lagrangian points at the end of the bar. What happens if you keep sending particles through the manifolds? What happens to the global potential? It changes. Then the galaxy is no longer symmetric with the bar. Now it's symmetric with the bar plus the spirals. So if you compute the global Lagrangian points, will not be in the extreme of the bars, will be on the top of the spirals. So you break the connection between the bar and the spirals. And then the spiral arms slightly disappear. When the spiral arms disappear, you recover the symmetry, and the Lagrangian points go back to the extremes of the bar, and then you have another outflow of particles through the manifolds. So this was the theory, and we have been checking that, and it's what we really see that is happening in the simulation. It's a single simulation. We need to check that in more simulations, but it's quite promising and exciting to finally see that this is happening in a pure self-gravitating n-body simulation. And as I said, I really need to say that Tony and Mercè Romero are the ones that are really leading a lot that, and of course Mercè is the guru of the manifolds for many years. And yeah, that's all. The summary. I talked a lot about Harkonnens. Hope you can use it at some point in the close future or in 2030 when we have the 2 billion or 3 billion CPU hours wasted. And invariant manifolds that, well, hopefully you will hear more about that, and you will see it soon more in the archive. And that's all.
Ask the people online.
People online.
Questions online?
Everybody is sleeping.
I don't think so.
No? Or they left without saying. Yeah.
How they generate it if it is the visibility of the tidal type, etc. I mean, how they generate is the model, baryonic physics models with the nature of dark matter.
Can we relate that?
I mean, no. If it's the generation, I mean, I guess you are gonna see how many tidal types you see, depending on the characteristics, different mass, etc. It's just I mean, and we have seen that you can find difference due to the nature of dark matter and due to the model of baryonic physics that is put in the simulation. So how do you relate those?
It's absolutely a great question, and it's also something that we have been struggling, and it's still not fully understood. So we have like till 2030 to try to figure out this before we get the observations. But some insights that we are starting to get is that because we are using many parameters, some of these parameters, and this is what is being shown also in the emulator, some of the parameters, like for example, the width and the length of the streams, can be more related with, I am inventing, I am not saying that this is, can be more related with the fact that you have warmer or colder dark matter than on the stellar feedback. But if you go to the specifics of the profile of the stellar halo, how fast it decreases the light in the stellar halo, maybe it depends more on the, that in fact it's the other way around. We have seen more or less that the stellar halo is more related with dark matter and the streams are more related with baryonic physics, but it's not conclusive the result that I am just saying, and we aren't studying it.
Yeah,
and
another question very
yeah.
But how, I mean, do you expect cell similarity or some kind of cell similarity between halos of different masses in the dark matter I guess from the Harian physics you don't. And can you use differences between halos of different masses to break or partially break or to help you with the regeneration?
It's absolutely. So the problem with that is that we will be able to do that in the simulation, but in the observation I am not sure if we will be able to do it. But yeah.
You can use
something
you
that
don't need to reach
yeah.
To distinguish the same. I don't know. I'm just
one thing that we have seen in this line is that to generate very visible streams that, for example, Auriga simulations do, you need some kind of pre-processing that makes the small halo to be puffier. So this part of the difference on the halos before info is already having a consequence on the stream formation. So you can see it indirectly. Yes, in the simulations you will be able to see directly differences between like self-similarity between different dark matter halos. No? But in observations maybe has an impact also. Yeah, everything is just science that is ongoing. So everything, there is nothing published from everything that I have shared. There is nothing published yet. Should do soon. Yep.
Related to the physics of dark matter, so when you use different masses, I guess it's just the initial power spectrum.
Exactly. Yes.
But when you use self-interacting dark matter or the other models, how do you implement the physics?
For the very, there are many ways to do self-interacting dark matter. The first approach that we will be using is coming from the Camila Correa paper 2022, in where she shows the dependence on the cross-section of self-interacting dark matter and if it is needed or not velocity dependence on the self-interacting dark matter interactions. We found that for a Milky Way mass and the dwarf galaxies mass range that we are simulating, we can use self-interacting dark matter that only has a cross-section, that is not velocity dependent. So that the cross-section is... Well, I am being very technical, no? Yeah, very technical. Yes, so it's introducing, so you introduce a new computation in where you take into account the neighbors and you account for the interaction that is getting with the neighbors, and you kind of slow down the dark matter with the kind of, yes. You need, obviously it depends on the number of neighbors, and you have to select how many neighbors you account for, and if it is too large, then you need again trillions of CPU hours, blah 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 blah. The time steps get very low. But we are going to do only two different self-interacting dark matters with two different cross sections that are within what is expected from the core CASP observations of dwarfs. That is 10 and 50 centimeter square divided by gram. And we do not modify the initial power spectrum. That we could. There are some models that also modify it, but no, we keep the cold dark matter power spectrum. Yep. Yeah. I know. We should modify it. We do it. We will do it. Next step. Yes. We have it in mind. Yes. Absolutely. It will be more. Well, 3 billion is the original. So if you give us more, we will use it. Okay, so I think we can leave it here. If online there is nobody. Yes.
I'm not from the scale, but I'm curious for this SPH, which kind of kernel function to use in the large scale stuff.
You are killing me totally because I have been working in AMR codes all my entire life, so I don't know. I am a user of SPH. Yes. So we use both with the same initial conditions to check if the results are dependent or not in the numerical approach. But the experts on SPH is the Japanese team that they are running it.
For AMR, you don't change the physics, you just
So
zoom in.
it depends on which physics you are talking about. So you can change the physics. Supernovae is also good physics. But yes, the AMR approach. You can also have different AMR approaches. There is the octal tree where you divide it with octs, but you also have the moving mesh that moves with the density. So there are different approaches. We use a fixed octal tree mesh. Yep.
Hello, online. So the difference in feedback schemes is of course more relevant, but how large is the difference, order of bandwidth between different codes, numerical schemes with the same feedback?
You can ask Ramon if you want. Okay, a lot. Yes.
Because in Arrakihs we had different numerical codes with also different feedback schemes, so we cannot distinguish.
the same feedback, only just the difference in
We didn't
numerical
try that
resolution.
in our.
Paper 2. But is it isolated? No, Ramon was not there. Ramon was not even born. No, in paper 2. No, we had a paper that was an isolated simulation in where we, same initial conditions, same feedback prescriptions, and you see that many things converge, but many others doesn't. So, but yes, the general ones.
Same resolution as well, I mean.
Yeah.
It's not the
Yeah.
definition of the same, okay?
Well, same resolution in the disk. So again, big difference come from the fact that AMR codes do a wonderful job in the CGM and in the creation of gas, while SPH codes struggle a lot on the gas physics and the multi-phase gas in the, yeah, exactly. So there are these SPH versus AMR differences.
The emulator that we're talking about is going to be able to distinguish, to also make predictions about the numerical code.
We have
we are going to trade with gadget and with process.
This is the question that we have a team now of big names on the emulations world that is joining almost every 2 weeks. And one of the big discussions is this one, how to compare different codes doing the emulation. And the idea we have now in mind is not final, is to develop 2 emulators, one for the Ramses, one for gadget, and then to make simulations that bridge between both, to see which are the differences and train another level in where can learn the differences between one and the other. Because you will have the same initial conditions run with colder matter in Ramses and in gadget. You will already learn the difference due to the feedback variations, and then the other dimension will be the code difference. But it's not trivial, and we don't even know if it is possible. But yes, in Dreams they use the same code. In Artemis they use Arepo. If I am not wrong. In Dreams they use both use Arepo. No. Emulations is interesting. If you want to join to the meetings, you are more than welcome.
You have to finish.
After your thesis. Good. So I think it has been already like more than 1 hour because we are started late. So I think maybe we can leave it here. So thank you. Hay una pregunta online. ¿Quién es? Who?
Can you hear me?
Yes.
No, because there is actually in the chat one question.
Oh, please read it.
So, it's by Marta Reina, and she's asking what about Gizmo and or fire physics? Are you planning to folding them into the Harkonens?
Hello, Marta. Hi. Yes, the idea is that we have people working with Gizmo. Our goal would be to have also the Agora initial conditions run with the fire-compatible physics. We are in fact doing that at the resolution of Agora, but it's true that we don't have now anybody committed to run fire physics with the resolution of Harkonens. So, if you're interested, Marta, please drop me an email. You will be more than welcome to run these models. We have also AIDA TNG being run with somebody that is not fully inside Arrakihs. So if you want to contribute, and as I said, we want to bridge between Agora and Arrakihs in this part of the collaboration. So you would be more than welcome to be on that if you have the physics in hand. Yep. Anything else? Then I think that we leave it here. Thank you. Thank you.
¿Nombres de halcones? ¿Significa algo?
Sí, o sea, son los malos de Dune. En la serie de Dune, en la peli de Dune están los Atreides, que son los buenos, que es el código para producir imágenes realistas, y las simulaciones son Harkonens, que es el hacer cosas con Dark Matter y simulaciones. Sí. Bueno, y tenemos Harvester, que es otra de las cosas de la película, que es el... Sí, o sea, todo está en Dune related. Sí. Total. Pues nada, sí, eso. Sí, vamos a ver. O sea, hay mucha energía y muchas ganas, pero vamos a ver si conseguimos los millones de este manera que necesitamos. De momento estamos en ello. Sí. Vamos a ver. Sí. Nada, gracias. Sí.
Lo estoy viendo por cuarta o quinta vez, con lo cual se me hace muchísima gracia.
¿El qué?
O sea, me lo leo cada 2 o 3 años.
Pues mira.
Yo
¡Ay, Ángela! Como nos vemos tanto por telecons, pensaba, pues se la ve. Hostia, tengo un cabello súper largo, lo sé. Sí. Un cabello. El resto. Hemos hablado de ello. Sí, ya hablaremos. Sí. Dime.
Yo pregunto, al principio cuando has puesto todas las diferentes simulaciones y demás, y una cosa que me ha llamado la atención y me ha chorreado un poquito, cuando decís el tamaño de la caja L,
Sí.
¿qué unidades habéis utilizado? Porque me ha parecido ver centimegaparsecs.
No, co-moving megaparsecs.
Vale, es que... Vale.
Co-moving. Son... No. Co-moving megaparsecs porque son los... en la simulación es útil que todo esté fijo y que no tengas en cuenta la expansión del universo, que es algo que va a ocurrir igualmente. Luego pues le pones co-moving y todo está fijo. Sí.
Vaya mierdón.
Ay, Dios mío, vaya mierda.
Dios mío, vaya mierdón. Perdón que vamos.
No lo has puesto, no me he enterado que me habías puesto el título.
Pues si llevas toda la charla con el micrófono. Si este está desenchufado.